Hello, in this session I'm going to talk about enlargement. Enlargement is about taking a figure on the XY plane and making it bigger or smaller. As an example, we can look at a figure, say a triangle. So let's say we have this triangle. The corners are at 3 points on the coordinate on the XY plane, and we know the positions of these 3 points. Now, in enlargement, we want to look at a transformation that will make this bigger. The matrix, this time I'll just write down an example of a matrix. Let me look at a matrix like this. 2, 0, 0, 2. Now, I'll explain in a moment how this matrix works. The idea is that if we take this matrix and apply it to each point on the corner of the triangle, it will transform those points to a new position. So let's try that and see what happens. Now I'll call this point A, B, and C. Alright, so point A is position 1, 1. If I multiply the matrix by this point, so we do row times the column. 2 times 1 is 1, 0 times 1 is 0. So it's 2 plus 0, which is 2. And you do it for the next row and this column again. 0 times 1 is 0, 2 times 1 is 2. So we have 0 plus 2, which is 2 again. So this point A would map onto this point, which is the 2, 2. I'll call that A point. Okay, so we have 1 point. Now let's do that for the point B, which is 2, 1. Okay. In the same way, we can multiply the matrix by the vector. 2 times 2 is 4, 0 times 1 is 0. And so 4 plus 0 is 4. And next row, 0 times 2 is 0, 2 times 1 is 2. So 0 plus 2 is 2. And 4, 2 is the new position. Now 4, 2, 4 is somewhere there, 2 is somewhere there. So 4, 2 is about there. That's the image for B. And last point, C, is 1, 3. So following the same idea, when we multiply this, we'll find 2 times 1 plus 0 is 2, 0 times 1 plus 2 times 3, which is 6. So 2, 6 is the image of C. 2 is here, 6 is about there. So C is roughly here. So those are the new points for the corners of the new triangle. And if I join those points, you see this is what you get. the triangle is enlarged. That's why we call this an enlargement. So what I've done is that I have simply assumed that let's say we are given this matrix 2, 0, 0, 2, and I multiply it by the x and y for each of the corners of the triangle, and then I find that when I plotted the new points for the corners and join them up to make the triangle, I get a bigger triangle. So from this exercise, we can see that this matrix has the effect of enlarging the triangle. We call this an enlargement matrix. But we really don't want to just take a given set of numbers and multiply it to see what happens all the time. So we want some idea about how this works in geometry. Right. So let's look at these figures, the big triangle and the small triangle. Let's think about the relation. Think about these pictures. Now I'm going to draw some lines from the origin to give us an idea of what's happening here. So let me draw a line from the origin to B. Now if I carry on this line, I will reach the image of B. Okay, I can actually join them up in a straight line. The reason is quite simple, because when I say calculated the image B prime from B using the matrix, you can see that what really happened here, because there are zeros down here, so what really happened was that the 2 for the x value is simply multiplied by 2, and the 1 is multiplied by 2. It's the same for the others. This matrix has the effect of multiplying the x and y value by 2 and 2. Okay, so all it does is that it takes the point 2, 1 and brings it to 4, 2. That's why the image and the point lies on the same straight line as the origin. Alright, if I now draw a line joining A to A prime, they lie on the same straight line as well. And similarly for C. Now we are beginning to see a pattern in this picture. And let's look a little bit closer at this line. Now, the coordinates of the image of B, or that means of B prime, is 4 and 2. Alright? That means that the x value of B, which is 2, is multiplied by 2 and becomes 4. Okay, if I think of this line, okay, this line and the x-axis forms a triangle, okay, and this line and the x-axis here forms another triangle. So it's as if we are looking at two similar triangles here, this one and this one. So if this side of the triangle is multiplied by 2, the 2 becomes 4. And this means that the line OB, when it becomes OB prime, is actually doubled in length. So that means that the line joining O to the new image of B is actually 2 times longer than the line OB. So really happens is that it's the same for all the other corners. If I think of the line OA and the line from origin to the image of A, you'll find that the distance of origin to the image is twice of the distance from the origin to the starting point A. So that gives us another way to think about enlargement. Alright, in fact we can actually have started from this way of thinking about it and then move on to the matrix calculation. So let's think about it this way. In an enlargement, what we are simply doing is that we have a figure, say a triangle. It can be another shape like rectangle or even a circle, which would be more complicated. Right, we have a figure like a triangle and we have a point, which is the origin in this example. And actually it can be other points, but we'll just look at the origin for now. Now, we call the origin the center of enlargement. So in this case, this is the center of enlargement. And there, and enlargement. And if I want to do an enlargement transformation on this triangle with O as the center of enlargement, if I want to enlarge it by 2 times, that means that if I have an enlargement factor of 2, got that? So let's say I have an enlargement factor of 2. Now I can actually do the enlargement geometrically without using the matrix or instead of the matrix. So what I would do is that from the center of enlargement, I would draw a line from the center to a corner of the triangle. And because the enlargement is 2, to find the image, I simply multiply this length by 2. So this line, I would double its length and I will come here to the new point, which I call B prime. So in this way I would get the image of B, alright, without having to use the matrix. In the same way, to find the image of A, I would draw a line from the center of enlargement to A and then multiply this length by 2 and I would arrive at a new point which I call A prime. And if we continue, we draw a line from the center to corner C and then double the length and reach that point which is the image of C. And then I can join up those 3 image points to get my new enlarged triangle. So this is how I could do it geometrically by drawing on the diagram instead of using matrix. So there are these 2 ways to do that and they give you the same results. And we need to really understand both ways to get it to work properly. So, and I'll just mention this again. I said just now that the center of enlargement does not have to be at the origin. For example, I could have a center at another point and I can still do the enlargement by drawing in a similar way. Except that if I have a center of enlargement that is not at the origin, then I cannot so easily do the same thing or calculate the same positions using a matrix. Alright, I have to do something more complicated. I have to there are one or two more steps that we must do before we can do this matrix multiplication. We have to do a translation somehow. So we'll look at that later in some examples, but for now I would just mention that it is important to remember that you can only do an enlargement using matrix multiplication for the very special case in which the center of enlargement is at the origin. Okay, and if the center of enlargement is at a point different from the origin, then you cannot find the answer by doing a simple matrix multiplication. Now, and another thing I should mention here is that in this example, what you see is that a figure, a triangle, becomes enlarged. It becomes bigger, and we have an enlargement factor of 2, and you could imagine that there might be, you can use other enlargement factors like 3, and that would give an even bigger triangle, or we can actually think of an enlargement factor which is smaller than 1, like half. What if the enlargement factor is half? The idea is similar, except that when you draw the line from O to one corner, for example, you would then multiply the length by half instead of 2. So instead of the line becoming longer, okay, if the enlargement factor is half, you would make the line shorter to half in order to find the image point. So if the enlargement factor is half, then the image point, say for B, would actually be at half the length, which is here. Okay, and if you do the same for O, for the point A, you find the position for half the length to A and half the length to C. Then what you get, if you then join the new points, is a smaller triangle. So what this means is that if you have an enlargement factor that is smaller than 1, you end up with a triangle that is smaller. So it's actually a contraction rather than an enlargement. But mathematically, we can still think about it, we can still describe it as an enlargement with a factor that is smaller than 1. Okay, so that's just a long way of saying that it's a contraction. And we get a smaller triangle. Now there is yet another special case or possibility about the enlargement factor, and that is if the enlargement factor is a negative number. So what happens if the enlargement factor is negative? Now to make things easy, let me I'll just put just label that triangle by half to remind us that the enlargement factor for that is half, and for that it's a factor of 2. So what happens if the enlargement factor is negative? As an example, let's think about an enlargement factor of -1. So -1, what does it mean? -1. Let's look at the line joining the center O to the corner B again. Remember that if I have an enlargement factor of 2, I should multiply OB by 2 to arrive at the image. So that means that if I have an enlargement factor of -1, I should multiply OB by -1. But what do we mean by multiplying a length by -1? Well, in this case, we have to use the ideas of vectors. if you remember from our earlier session on vectors, a vector is something that has a length and a direction. So we can think of OB as a vector pointing from O to B. And if you multiply this by -1, it simply means that you change direction. So if you multiply by 1, it's still the same length, but if there's a minus sign, like -1, you simply reverse the direction. So instead of going from O to B, you go in the opposite direction by the same distance. Alright, so same distance but opposite direction. So this means that my new my image point for B is now here. I'll call that B double point. So once we get this idea, we can easily find all the other image points. So let's do it for A. Right, so OA is from there to that corner. If I have an enlargement factor of -1, instead of going from O to A in this direction, I should go in the opposite direction for the same distance. So that's my new image point A double prime. Finally, to find the image point for the corner C, alright, I would go in the opposite direction again for the same distance. So C double prime is my image point for C. And now if I join the corners, I get my new triangle, I get my image triangle. And if you compare this image triangle with the original ABC, you can see straight away that there is, you can see how they are related. Obviously, the original triangle is inverted, alright, it's flipped over when you come over there. So it's an inversion. We can think of it as an inversion through the origin. It's simply, you can simply imagine that it gets contracted towards the origin and then it expands again in the other direction. So the shape is actually, the triangle is actually flipped over. Whereas C was pointing up, or at first, it is now pointing down. So you can think about it as an inversion. This is for an enlargement factor of -1. Now you can also think of it as a rotation. Look at this triangle. If I rotate it by 180 degrees around the origin, I will arrive at this same image. So in fact it's a rotation by 180 degrees about the origin. So we have something interesting here. An enlargement that has a factor of -1, alright, is the same as an inversion about the origin, and it is the same as a rotation by 180 degrees about the origin. Okay, so this is one of the interesting features of enlargements. The next transformation I want to talk about is shearing. So what is shearing? Let's look at this example. I have a rectangle here. Now, imagine that this rectangle is a piece of rubber sheet that I can grab onto and then I can pull and stretch. Alright, now imagine now that I'll call the corners A, B, C, D. So imagine that I grip onto the side CD with one hand and the side AB with my other hand, and I pull CD one way and I pull AB the other way. So I'm not going to rotate it, right? I'm not going to do a rotation. I'm simply going to grip onto the top and the bottom and pull it this way. Okay, so I'm giving the rectangle a hard time. Alright, I'm really stretching it in a funny way. Now what happens now is that to make things simple, I'm not really going to move the side AB, I'm just going to hold on tight to it, but I'm going to, when I grip onto the other side DC, I will start moving it to the right. Okay, so I grip on tight to this side and I pull this. So what you might imagine is that the shape changes. It would probably get all distorted and twisted. But I'm just going to think about it very simply as changing shape from a proper rectangle to a shape that looks slanted, like that, to a parallelogram. So this is what we mean by shearing. It's being stretched this way. So not a simple pulling kind of stretch, but the shearing. Now in mathematics, we think of a shear transformation with one or two simple rules. So for example, if I think of a shear transformation on a figure in the xy plane, okay, so this would be a shear in the x direction, for example. Then from what you can see here, for a point on the x-axis, the point does not move. So in a shear transformation, points in the x direction, I'll put that in x, points on the x-axis stay, okay? They don't move. Whereas points which are away from the x-axis, like D, they move in the y in the x direction. Now, and they move in a way that follows a rule. So what it means is that if I have, say, a point there, which is halfway up the rectangle, so not so far from A, then this point moves to that point. Alright, it moves by this distance. And if I move further away to, say, this corner D, this point moves to that point. So D moves further away than to the right than a point halfway below, which moves actually just half the distance. So a point that is away from the x-axis will move along the x direction, and the further away it is, the more it moves. So that's the rule. Now then the next rule tells us how far it moves. So how do we know how much D moves? Well, like the other transformations that we've learned, if you remember, when we learn about rotation, we need to know the angle, alright, to know how much you rotate. When we learn about enlargement, there was an enlargement factor which tells us how much you enlarge. So in the same way, when we learn about shearing, there is a shear factor. Now, I'll just make up an example. Say, in this case, I have a shear factor of 2. Let's see how to use this shear factor. I'm going to put in some numbers for the positions of A, B. Let's say B is at 3 and CD. Right, let's say that's just 1. Alright, so if I have a shear factor of 2, what it means is that if I look at point D, which is away from the x-axis by a distance of 1, alright, so the distance of D from the x-axis is 1, then if there is a shear factor of 2, I must move D along the x direction by a distance that is equal to 1 times 2. 1, which is the distance from the x, and 2, which is the shear factor. So let me write this down. So when you do shearing in x, okay, a point moves by a distance that is equal to its distance from the x-axis times the shear factor. So this is how we can think about it geometrically, how we can think about it if we actually want to use diagram and drawing to find the new position or the new shape of a figure when you do the shearing. Right, in the same way that I've talked about rotation and enlargement. Okay, so this gives us a nice way of doing it with diagrams and drawing. So like the other transformations that I have talked about, we can also do it using a matrix. So what does a shear matrix look like? Now imagine that I start with a matrix with 1 and 1 along the diagonal. Then a shear in the x direction with a factor of 2 has a matrix that looks like this. I would put the factor of 2 there and a 0 here. Now if you have looked at this session and the last one on matrix transformation, and maybe the one before that, you may start wondering how we actually make up all of these matrices. Surely you cannot be expected to memorize all of them, and even if you do, you may wonder how they come about. How do people actually make all this up? In another session, probably the next one, I shall explain how you can remember all these different transformations, how you can understand them and probably derive them if you actually forget. So for now, I have to ask you to be patient and just take it that this matrix is given, and we just want to see how we can actually use this matrix to get the same result which we got by drawing. So if I look at the point D, for example, position is 1, 1. Now if I want to find the image point of D under shearing, I can multiply the matrix by the vector. If I multiply the matrix by the vector, I have 1 times 1, right, row and column. So 1 times 1 plus 2 times 1. And the next will be 0 times 1 plus 1 times 1. And what we see here is that the y position of the image stays the same, right? It's still 1, whereas the x position has moved. At first it was 1, it was here. Okay, that's the x position of D, but it has moved along the x because 1 has changed to 1 plus 2, and 2, if you remember, comes from 2 times 1. Okay, so the 2 here actually came from the 2 times 1. And as I explained just now, the distance that it moves is equal to the shear factor multiplied by the y value, multiplied by the distance of D from the x-axis. So it works the same way when you do a matrix multiplication. Okay, and the answer is 3, 1. So that's the new position of D prime, of the image point. Now the figure as I've drawn it is not quite accurate because 3 would really be here. Okay, so if I draw this accurately, my D, the point D should have moved all the way to somewhere there. Okay, but just take this as an illustration, as a picture to give you some idea about how things work. Okay, and I should mention one or two more things about shearing in the x direction. In this example, the shear factor is 2. Now what if the shear factor is a negative number? In this example, what you see is that the top of the rectangle moves to the right. So if the shear factor is say -2, it would actually move to the left instead. Okay, so that's possible. Alright. Now, another thing about the shearing is this. What if I have a rectangle that is below the x-axis, and let's say my shear factor is still 2. Now we know that if the rectangle is on top of the x-axis, the top side of the rectangle would move to the right, okay, and the side touching the x-axis will stay. Now if the rectangle is below the x-axis and my shear factor is 2, a positive number, then it is the lower side of this rectangle that will move, and it will move to the left. Okay, the reason is that we think, whereas the y value of this corner is 1, the y value of that corner is actually -1. So the distance that it moved, if you remember, is actually the y value multiplied by the shear factor. And because the y value is a -1, you have -1 times 2, which is -2. So this means that if the rectangle is below the x-axis, this lower side would actually move in the opposite direction to what happens if the rectangle is on top of the x-axis. That is shearing in the x direction. There is also shearing in the y direction, which is very similar. So I'm just going to quickly say what is similar. So what I have here is a rectangle which is touching the y-axis, and if I have shearing in the y direction, this side of the triangle would stay fixed and that side moves. So when it moves, it changes shape like before, and it looks like this. So it's very similar to shearing in the x direction, except that we're now doing it along the y-axis. And there is also a matrix for that. Say if I have a shear factor of 2, the matrix would look very similar to the one before, but instead of having a 2 in that place, I now have a 2 down here. So that's my shear factor. Okay, and we just do the multiplying in the same way. And I'll just very quickly mention one more thing. Stretch. XY plane again. Now imagine a square. Let's say that's 1 and that's 1. Just a simple square with side 1. Again, think of this as rubber sheets, and imagine that I grip one side with one hand and the other side with another hand, and I start pulling it this way. But this time I'm not shearing it, I'm stretching it, I'm just pulling it this way. And then this rubber sheet, since it's rubber, it can be stretched, it becomes longer. So I get a new shape like that. So this is yet another kind of transformation that we can have. Okay, and we have a factor again. So let's say our stretch factor is 2. So if the stretch factor is 2, it simply means that it becomes 2 times longer when I stretch it. So if this is 1, then this comes to 2. Okay, so this is fairly simple compared to shearing and enlargement. It's just in one direction. And the matrix is also simpler. If I have a shear factor, stretch factor of 2, the matrix will look like this. 2, 1. Right, where that number 2 comes from the stretch factor. And you can easily check. Let's say I look at that corner, A, which has coordinates 1, 1. Now if I stretch it, I know that it comes to this corner, A prime, which has coordinates 2, 1. And let's check this out with the matrix. If I multiply this row by this column, I'll get 2 times 1, which is 2, plus 0 times 1, which is 0. And for the next row, I have 0 times 1, 0, plus 1 times 1, which is 1. So that's the correct coordinates for A prime. And that is our stretch matrix. We'll stop here for this session. See you next time.